Hello students, today we are going to study about the design of heat slab of retaining wall. In previous class, we have designed the toe part of the retaining wall. In the same line, same method we are going to follow for the design of heel slab also. So initially we will calculate what are the loads coming over the heel slab, and we will calculate the moment at the end of the heel slab which is being connected to the vertical member, that is stem, and there we are going to calculate the moment, and for that moment we are going to calculate the reinforcing bars required. So starting with this, we will calculate the downward force or the weight of the soil in this design. So we have first one to download the downward. We have first one to calculate the downward weight of the soil and downward weight of the heel slab. These are the two loads acting in downward direction, and third one is the soil pressure which is acting in the upward direction. So downward weight of the soil of height 5.6 meter. Here I am not going to consider entire height of this retaining wall because soil will be above the heel slab. This heel slab is carrying the soil of height 5.6 meter. So H1 we are going to consider here. Second load is the self weight of the heel slab, and third one is the upward soil pressure. So first one we will calculate weight of the soil. Density of the soil is 1.6, having the height 5.6, and 1.65 is the length of the heel. So this will be 147.84 kilonewton. This is the load acting. This is the load acting on the heel slab, and where it is acting, as it is the weight of the soil, it will be acting exactly at the center of the distance 1.65. What is 1.65? That is the length of the heel part. So 1.65 divided by 2. So that will be 8.25. It is 820.825. So it is 825 mm. So 147.84 kilonewton force will be acting downward direction, and it is acting at a distance of 825 mm from point B. Where is the B point? It is here. So in the figure also you can observe where is the B point. I will show. So B is here. C and D, these two are the portion of the stem. This is a toe part. This is a heel part completely. So here I am going to calculate the moment for the length of 1.65 meters. Right. So first one we have calculated soil weight. Then self weight of the heel slab. So thickness of the heel slab is 400 mm. So 0.4 into 25 concrete density, and length is 1.65. So the self weight of the heel will be 16.5 kilonewton. And again it is acting at the center of the heel. So it is 825 mm from the B point. So total downward force is equal to 147.84 plus 16.5. So it will be 164.34 kilonewton, and they are acting at the same point. So 825 mm from B point. Now we will calculate the upward soil pressure at point B. So again similar triangle we are going to use here, or maybe by interpolation you can obtain the pressure at the point B. So it is your convenience. You can go for the calculation of the pressure at B point with the interpolation method, or it may be by the similar triangle method. Whichever is simple to you, you can use that method. So I have done here with the both methods. So again I have used the interpolation method after using this similar triangle. So by the interpolation, this is the trapezoidal pressure diagram. So here is the maximum, here is the minimum, and I need to calculate the pressure at point B at a distance 1.65 from this point, 2.88, this edge. So 2.88 plus, by interpolation I am calculating here pressure at B. So it is equal to 2.88 plus 141.34 maximum minus minimum, that is 2.88 into 3.135 minus 3 minus 0. So 3.135. How I obtained this? This is the remaining portion. So total portion is, this portion is 1.65, right? What is this portion? This is total, it is 3 meters, right? So 3 meter minus 1.65 meter, that will be 1.35 meter. So I will obtain now here the pressure at B with the interpolation 79 kilonewton meter square. So it is at point B. Now I will calculate the force. So it is total load I have calculated. Downward load, it is 164.34 kilonewton. Then I have calculated the pressure at B point. So total upward soil pressure I will calculate. I have calculated at B, it is 79.79 kilonewton meter square. Now I need to calculate vertical force, that is the upward soil pressure calculated, but I need to convert that into force. So when I want to convert that into force, I have this triangular portion and a rectangular portion. This rectangular portion of length 1.65 and this is 2.88, and again there is a triangular portion of the length 141.34 minus this distance, that is 2.88, that will be 1.3. This remaining portion I need to calculate. So I have calculated that as 79. So this will be total, it is 79 at this point. So 79 minus 2.88, I will obtain this part x. So that will be calculated here. What is the value of x? Then again the triangle, it is base and length is 1.65 again. So base height into half, that will be the area of this triangle, and rectangle it is 1.65 into 2.88. So I have calculated the same thing here. So upward soil force is equal to 2.88 into 1.65. That is rectangular portion. So it is 4.75 kilonewton. Where it is acting, it is exactly at the center of this. So it is 1.62. So it will be 825 mm from the point B. And similarly, I will calculate for the triangle. It is half base. As I said, it is 79 minus 2.88. It is a base into height. Height is 1.65. So area is 62.8 kilonewton. I will obtain total load it is. And where it is acting at a distance h by 3 from the base. So base it is at B. So h is 1.65 by 3. I will obtain the distance. So it is 1.65 by 3. It is 0.55. So I have obtained now three forces. One is downward force. Total downward force I have calculated. It is acting exactly at the center this. So it is at a distance of 825 mm from B, and force is 164.34. And next is the upward soil pressure, soil force. One is the rectangular one, and another is the triangular one. So with respect to that, these calculations I will obtain what is the total force at point B. So total force point B is equal to this 164.34, and these two are the negative forces which are acting in upward direction. So it is 62.8 and 4.75. So if I calculate total or net force at point B, then it will be the shear force. So shear force at point B is 96.79 kilonewton. So this will be used in the check for shear. So now I will be calculating the bending moment, as I have three forces with the distances from the point B, right? So first one is 147.8 acting at a distance of 0.825 plus 16.5 into acting at a distance of 0.825. So this one it is here 4.75. This one 4.75 into 0.825. It is acting at a distance of 825 mm, 825 mm. And last one is this triangular portion. So it is 62.8 into 0.55 acting at a distance 0.5. So 147.8. Actually, I have clubbed these two in the initial calculation here. So this is initial calculation where I can club this and I can calculate, because these two are acting at the same point. Or else I can calculate them separately. This into this distance, this into this distance. I have done it in a simple manner, but I can club these two and I can calculate. So total moment, or let's say net moment at B is 96.8 kilonewton meter. So now I will calculate ultimate moment. It is 1.5 times this moment. So it will be 145.2 kilonewton meter. So I will check now for the depth requirement. D required or effective depth required is equal to under root mu divided by Ru max into B. So mu is 145.2 kilonewton. So it is 10 to the power 6 kilonewton meter it is. So convert that into Newton mm. It will be 10 to the power 6 divided by 2.76, that is Ru max into B. 1 meter distance we will consider, length we will consider. So it is 1000. So depth required is 229.4, but what we have provided is 340. So I can say sufficient depth is being provided. So now I will calculate the AST for the moment and this depth, provided depth. So it is 0.5 into FCK divided by Fy. So it is 0.5 into 20 by 415 under in bracket 1 minus under root 1 minus mu divided by FCK BD square into B into D. So substituting the values of this, 4.6 into mu, it is 145.2 into 10 to the power 6 divided by B 1000 D square, it is 340 square into FCK 20 and into BD 1000 into 340. So AST required is equal to 1285 mm square. Then I will be using the 16 mm bar here. So using 16 mm bars, spacing is equal to 5 by 4 into 16 square. That is area of one bar divided by total cross sectional area of the bars into 1000. So spacing is equal to 156 mm. Let's say spacing of the 16 mm bar is 150 mm from center to center. So I have already calculated the shear force. As I said, it is 96.79. So ultimate shear force is equal to 1.5 into 96.79. So it will be 144.8 kilonewton. So now I will calculate the percentage of steel reinforcement provided. It is 100 into 1340 divided by 1000 into 340. So it is the AST provided with respect to this calculation, means 150 mm is the spacing provided for the 16 mm dia bar. So if I calculate the AST provided, then it will be 1340. You can calculate this. So it is small AST divided by BD, or it is it is not small AST. It is total AST. Matlab it means total AST provided divided by B into D. P is 1000, D into 340. D is 3 D, that is the effective depth is 340 into 100 percentage. So I will obtain PT percentage as 0.39%. So I will check what is the value of resistance of the concrete or shear resistance of the concrete stress. It is tau UC. So tau UC for M20 grade of concrete for the percentage PT equal to 0.39. I will check from IS 456 2000. So it will be 0.427 Newton per mm square. So tau UC I will obtain here, and then I can calculate VU, that is the resisting shear force of the concrete or shear resistance of the concrete. So it is tau UC into B into D. So tau UC is 0.427 into B 1000 into D. D is 0.34, or it is 340 by 1000. So I will convert that into mm. So 340 by 1000 I will write. So it will be 4 divided by 1000 is written here to convert this value to Newton to kilonewton. So it is 145.25 kilonewton, or else it is 145.25 into 10 to the power 3 newtons. So this is very much, or it is greater than VU. VU calculated is, here we have calculated VU, it is 144, but VU this is the V ultimate shear calculated is 144.8, but VU calculated is 145.25. So it is greater than this. So I can say that the heel slab is safe in shear. So after this, we'll provide the distribution steel. Distribution steel is equal to 0.25 into 1000 B into D. So it is gross area. B is 1000, D is 400 divided by 1000 and divided by 100, because it is 0.25%. So 0.25% is used for HYSD bars and 0.15 is used for MS bars. So it is 4 on 5 steel, so it is 0.25%. So percent means it is divided by 100. So I will obtain the distribution steel to be provided is 480 mm and 480 mm square. So using nominal reinforcement here, that is area of I will use 8 mm dia bars and I will provide the spacing of 100 mm center to center. So after this, we will design the stem part. As we know, stem is a vertical member. So what are the forces acting on the stem is downward force of the stem itself, but that will not be considered because it is vertical member, and I will consider only the horizontal force which causing the bending movement, or which will make the stem to bend, or which causes the stress inside the stem. So that is the horizontal earth pressure which is acting on the stem. So I will calculate that, and if I multiply that by the centroidal distance h by 3, then I will obtain the mu distance. So this calculation is been already done. So again we will calculate 1.5 is the ultimate moment. So moment is, it is area of the triangle into h by 3, that is the distance where this force is acting. So if I draw a triangle here, so this is the pressure diagram. This is the force acting here, acting at a distance h by 3, right? So this is gamma h1 into Ka, and if I want to calculate the total force, it is area of this triangle. So area is half, this half into base, this is the base, into height. So this will be the area, and it is acting at a distance h1 by 3. So that will be the moment. So ultimate moment means it is 1.5. So I will get the ultimate moment is equal to 234.15 kilonewton meter acting from the bottom or base point B. So total depth what we have provided at the stem is 350 mm, and effective depth I will calculate as we have provided 60 mm cover, effective cover. So that effective depth of the beam at the bottom of the stem is equal to 350 minus 60, it will be 290 mm. So with this calculation, that is mu and d calculation, I will calculate the AST required. AST required is equal to 0.5 into 20 divided by 4 on 5 into 1 minus under root 1 minus mu by FCK BD square into BD. So substituting the values here, I will obtain the AST required. It is 2797 mm square. So let's provide 20 mm bars because it is vertical member, so it carries larger load, horizontal pressure. So 20 mm bar I will use here. So provide 20 mm bars at a distance of 110 center to center. So what is the provided area now? Provided area of reinforcement. This 110 we can calculate, that is the spacing of the reinforcing bars. We can calculate it separately. So with this data 20 mm bar and 110 mm center to center spacing, I will calculate the AST provided. So AST provided is equal to 2856 mm square. Then LD is the development length. What is the development length? Initially I have given the formula. It is 47. By the simplification we obtained this as 47 into 5. 5 is the diameter of the bar, here 20. So LD is equal to 47 into 20, that will be 940 mm. Here what we need to uh, concentrate is, we cannot completely give the reinforcement to the from the bottom to the top, because it is on cantilever member, and at the top of the stem very less pressure is acting, or the bending moment at the top of the stem is zero, right? So we need to curtail, we need to cut certain amount of reinforcement there. So extend the bars for the length equal to the development length 940 mm into the base slab, means this 940 mm of distance, or this much length of the reinforcing bars are to be extended into the base slab. These vertical reinforcement will be there, and these reinforcements should be extended in the base slab to a distance of 940 mm. That is the meaning here. And after this we'll study about the curtailment. So every third bar is continued up to the end of the toe to serve as a toe reinforcement. Means we cannot if you want to provide the toe reinforcement and the stem reinforcement of same diameter bar, then we can continue this it is better to continue these vertical reinforcing bars to till the toe end point. After this, it is about the curtailment of bars. So curtailment point means where we need to cut the reinforcement bars. It is by the experience or the calculation, it is 0.79 h1. So 0.79 h1 from the bottom, what will be the distance? It is 4.4 meters. So 0.79 into 5.6, it is 4.4 meters. At this particular point, what is the EST we will calculate? So this is the distance, means this is the height of the stem considering, and what will be the moment at this point we will calculate. So mu is equal to 1.5 into density is 16 into 4.4 is the distance. It is half base into height. Base is gamma Ka. This 3 is h by 3, and here 1 by 3 is K, and this 2 1 by 2 is this is half. So here it is completely the area into h by 3, and this is K value. So it is 1.5, it is the ultimate moment calculation. So at this point, that is at 4.4 meter, what is the bending moment to obtain? It is 113.6 kilonewton meter. So which is almost half of the maximum ultimate moment at the bottom. So we have calculated the ultimate moment here. So ultimate moment calculation, we have 234, right? It is at the bottom, but at this particular point it is 113. So 113 into 2, it is almost 226, right? So it is almost half of this moment. So as the moment is almost half at the distance of 0.79 h1, so I will cut certain reinforcing bars. So I may provide, as the moment is very less or it is reduced to half at this point at distance 0.79 h1. So I will remove half of the reinforcement bars at this particular point, as it is half of the ultimate moment at the bottom. So total depth is at 4.4 meter. What is the depth at 4.4 meter? I will calculate. Again, it is by interpolation 200 mm at the top, and at the bottom this is a triangular portion. So 200 mm is the rectangular portion, that is at the top, and bottom it is 200, plus what is the distance remaining? It is 150 into 4.4 by 5.6. It is by interpolation. I will obtain the depth of the stem at 4.4. Please calculate it correctly. What I am explaining here is, okay, I'll show here from the figure itself. So coming back to this figure, so this is the point CB, right? So here what is the distance? At the top it is 200, right? Here it is 150 plus 200, so it is 350. I need to calculate what is the depth at the distance. I will write here. So I need to calculate what is the distance at a height of 4.4 meter here. In this section, what is the moment, or what is the depth I need to calculate? Moment is been already calculated. Now I want to calculate what is the depth here. Okay, we will calculate the depth. Okay, it is completed. Okay, total depth at a distance or at a depth of 4.4 meter is by interpolation 200. At the top it is 200 plus 150 into 4.4, that is the remaining distance where we want to calculate, and the remaining total height is 5.6. Top to bottom it is 5.6 meter. So D is equal to 318 mm. So effective depth is equal to 318 minus 60 cover, effective cover. So effective depth is equal to 258. So at this particular portion, what is the EST? I will calculate. So EST is equal to 0.5 FCK divided by Fy in bracket 1 minus under root 1 minus mu by B FCK BD square into BD. So substituting these values, I will obtain the value of EST. So EST can also be checked here. So total right? If I make it half, so it will be 1371 mm square. Means as the moment is reduced to half, here the AST also gets half, or amount of steel required is also half at this particular distance. So I will consider 4 meters instead of 4.4 meters. I will consider 4-meter distance, and I will curtail the alternate reinforcing bars. Actually, by the calculation, I need to extend these bars from bottom to top, here to here, here to here, here to here, but at a distance 0.79, as we have given here, at a distance 0.79 h, the moment gets reduced to, or the bending moment reduced to half, or reinforcing bars required at this particular distance is reducing to half. So I will curtail, or I will cut the alternate reinforcing bars here at a distance of 4 meter from the top here. So as I curtail these bars, what will be the spacing? So spacing provided here is, as I said, provide 20 mm reinforcing bars at 220 mm center to center at 4-meter depth here. And as I curtail these, so it is going to increase here, right? But as I'm providing alternate bars here, so this is going to reduce again. So here to here it is 220 mm, but I am providing, or I am curtailing the bars here at this particular junction or this particular distance. So it will be now half of this. So it means it is 220 mm from here to here. So in, if I insert one more reinforcing bar, so it will be half. So spacing at this portion will be 110 mm center to center. So this is the AST required at the bottom portion and top portion for the stem. So after that we are going to provide the distribution steel. So distribution steel is 0.212 divided by 100.12% of BD, that is gross area. So gross area is, length is 1000 mm we are going to consider, and depth or width is, it is average of top and bottom, it is 200 plus 350 divided by 2 into this is the D and this is the L or B, let's say. So it is 1000 into 350 plus 200 by 2 into 0.12%. So it will be 330 mm square minimum AST required. So front face I will provide, in the front face means away from the soil, I will provide 330 into 2 by 3, that is 220 mm square of reinforcement. Out of this, it means out of this 2/3 of reinforcement will be provided in the front portion and remaining will be provided in the back side. So provide 8 mm bars at 220 mm center to center at the front face, and same 8 mm bars will be provided at a spacing of 440 mm at the rear face. Means rear face means towards the, or it is near to the soil. So but in the opposite direction of the soil, or it is away from the soil, it will be 220 mm spacing, larger number of reinforcement bars will be provided, but near to the soil the spacing will be increased to 440 mm center to center. So this is about the design of toe part, heel part and stem part. So students, go through this, understand this. In the next class we will design the shear key that is to be provided. Thank you.